I will just start. It's a great pleasure to be back in Taiwan after 12 years. Yesterday I dug out some photos from my previous visit 12 years ago. As you can see, some things are changing. The airport is no longer called Shanghai. I was 12 years older. It didn't seem to be very good. All right, this one. Good, thank you very much. Yes, so the airport is no longer called Chiang Kai-shek, and I'm 12 years older. But other things remain the same. We still have this pesky problem called the hierarchy problem. Some people may just choose to ignore it, but it's still there. Yes, so of course we know that the Higgs is not protected by any symmetry, sensitive to any new physics at any scale. Yes, so we don't understand how it remains so light. One of the simple solutions that people have been exploring over the last 15 or so years is the idea that, well, the Higgs is actually not an elementary scalar, but a composite, and that's the reason why it is not sensitive to very high scales. In fact, there are no elementary scalars in theories. And then the question is, so how to make a theory like that work? So the most naive assumption would be that there's a scale of compositeness lambda. At that scale, you expect a lot of new particles to show up, like in QCD, around lambda QCD, there are many new particles. So that scale could actually not be very low, because those new particles will give you dimension 6 operators suppressed by the scale of those particle masses. We know that the bound on dimension 6 operators from LAC in general is around 5 to 10 TeV. So we know that this scale of compositeness cannot be like 1 TeV. It has to be more like that. So then there's still a problem. By just declaring the Higgs to be composite, you don't quite solve the issue of why the Higgs is light. Yes? Because in that case, the mass of the Higgs, in best case, would be a loop factor below this 10 TeV scale, which is still, quite a bit too high. That's about 100 times too large. So that is what is usually called the little higher. So basically, all the model building in composite Higgs models goes into trying to resolve this last factor of 100. Yes? So in order to try to do that, what people usually assume is that the Higgs is also a pseudo-Goldstone boson. So the expectation is that whatever that strong dynamics is that produces those composites at the scale of 10 TeV also has a global symmetry, which is spontaneously broken. And so there will be a spontaneous breaking of the global symmetry, which will produce some Goldstone bosons, and the Higgs could be identified with some of those Goldstone bosons. Okay. So the global symmetry breaking scale, due to the strong dynamics, is usually denoted by F, and the cutoff scale, the scale of compositeness, is lambda, and in most strongly interacting theories, there is a simple relation between the cutoff scale of where the generic composites show up, and the scale of chiral symmetry breaking given by naive dimensional analysis, that there is a factor of about 10 between. Okay, so the expectation then is that the global symmetry breaking scale is at around the TeV, the cutoff scale is 10 TeV, and if the corrections are actually given by F over 16 pi squared, then the Higgs could be an. But that, of course, will require that there will be some new particles showing up at 1 TeV rather than at 10 TeV. So the key ingredient in what is generically called composite Higgs models is that at this 1 TeV, a few new particles show up. They are special. They are called the top and the spin 1 partners. And those will be the ones that will get rid of the quadratic divergence between 1 TeV and 10 TeV. Yes? And then at 10 TeV, it's just generically, it's a composite theory, so there's no more elementary scalars. So at that point, you don't worry about it. Okay. And then, of course, you still have to explain electroweak symmetry breaking. So there has to be some form of explicit breaking, yes, that will misalign the embedding of the unbroken global symmetry inside the bigger global symmetry. Okay, so how should this explicit breaking work? Yes. So the problem, of course, is that generic explicit breaking will, again, reintroduce the quadratic divergence of the Higgs potential. So that's has to be something very special. And this is, where, that has been the main idea 15 years ago, the idea of collective symmetry breaking, where we are postulating there is no single explicit breaking term that is completely breaking the global symmetry, but you need at least 2 or more of these explicit breakings to give a mass to the Higgs. Okay, so then, because you have to have at least 2 of these insertions, that will soften the divergences and make the potential either finite or log divergent. Okay, so the simplest example of this collective breaking can be explained really on one slide. Yes, this you take. This is just a simple example model. This SU3 mod SU2. Yes, so there's an SU3 global symmetry broken to SU2. Then the Goldstone bosons are these off-diagonal generators. Yes, so you construct the corresponding Goldstone boson matrix. Yes. And what you want is to somehow ensure that there is this SU3 global symmetry that is maintained also in the interaction that will produce the top Yukawa coupling. So you enlarge the standard model fermion doublet, for example, the left-handed top and bottom doublet to a triplet. Yes. So this is where the top partner is coming in. Yes. This is again, the special particle that will, show up at around 1 TeV if you are lucky. Yes. And then get rid of the quadratic divergences. Yes. And then what you write is, you write a Yukawa coupling, yes, of this form, and you can see that this has a very special form. Yes. The first term is completely SU3 invariant. I copied it over here. The first term is completely SU3 invariant because psi is a triplet, H is a triplet. There's no explicit SU3 breaking here at all. Yes. So if I only had this term, there would be no potential generated for the Higgs at all. The second term, yes, this is very SU3 breaking because I just took here this T, this is the component from the triplet. Yes, so this is very SU3 breaking, but it doesn't contain the Higgs at all. Yes. So if I only turned on the second term, again there would be no Higgs potential generated because even though it's SU3 breaking, it doesn't depend on the Higgs. Only if you turn on both of these terms at the same time will you actually generate the potential. And the fact that you need both of these terms at the same time will tell you that the divergences are actually going to be softened compared to what you're expecting. Okay? So from this symmetry point of view, it's pretty clear why it has to work. Again, once you go ahead and expand it in terms of the components, it will look like a miracle. Yes, it will look like there's a cancellation here inside the usual standard model loop with the top and cancellation between the top part. So from this point of view, it may look like a miracle, but again, from the point of view of the underlying symmetry, it's pretty clear that there's a good reason for this cancellation. Okay? So that's the idea of collective breaking. And then one more ingredient in general about composite Higgs models is this idea of the minimal composite Higgs. So this is the most commonly used example for the group theory that is giving rise to the most natural symmetry breaking pattern that can incorporate the standard model with the custodial symmetry. So this SO5 broken to SO4 is the smallest group structure that is actually going to contain an SU2 right custodial symmetry group that will protect the e-parameter from line correction. So this is the model that people usually are trying to use when they are talking about composite Higgs models. Okay, so that's really great. So, of course, again, as I was emphasizing, the main ingredient in these composite Higgs models eventually is the presence of the top partners and the spin 1 partners, the ones that are actually going to cancel the quadratic divergences, the particles that have to show up at around the PV split. Yes? And of course, as you probably have heard, the LHC hasn't discovered this top partner. So the bounds are starting to become stronger and stronger, and you can see, of course, depending on the details of what exactly the branchings are, there are bounds that go all the way up to 1.3 TeV, starting up from around 700. So this is starting to look pretty bad for composite Higgs models in general. And the same thing for the spin 1 partners. Yes, so
So there would be corresponding W prime and Z prime particles that would be responsible for cancellation of the quadratic divergences from the standard model gauge bosons. And as you can see, the bounds of these are starting to be at around 2.53 degrees. Yeah, it's not very encouraging. So one of the directions that we tried to explore recently with my students off the Taiwan and former student Sal Lombardo and Gabe Lee, who is a postdoc at Cornell and also part in Korea, and Sung Lee, who is a Korea university, is to explore the possibility that maybe the reason why we haven't seen these top partners and spin-on partners is because they're actually harder to find than usually expected. And the idea that we were pursuing is that maybe these top partners and the spin-on partners are actually not quite ordinary particles, but they would be forming a continuum with a gap. Okay, so this is sort of similar to the direction that people were pursuing around 10 years ago, this idea of sort of unparticle-like like states. Yes, so for example, Giacomo, student somewhere here, yes. So he has written a lot of very nice papers with John on these kind of ideas in general, and also Sinchia was working on related ideas. But again, what we are trying to say is that, okay, maybe the top partners are not ordinary particles, but they are actually going to form a very broad continuum, which is much harder to see at the other end. Nevertheless, from the point of view of the cancellation of the quadratic divergences, they would just play exactly the same kind of role as the ordinary top particles. So here's a little cartoon, yes. So in a composite model, yes, you would expect power of bound states, or there are extra-dimensional versions of them. There would be a power of KK modes. So this is how usually the expectation is for these composite top partners. While in our model, what you will have is we will have the standard model particles as ordinary particles, but there would be a gap then, and at some point there would be sort of a very broad continuum starting, which would still possibly be canceling the quadratic divergences, but of course, since it's a continuum, many of the searches would be much harder to perform at the IFC. So here's a little bit of a roadmap of what are the kind of things that people have been considering. So these are the kind of ordinary composite Higgs models, or maybe supersymmetry, that people have been pursuing. Now, in general, there was the story of unparticles, but of course, those are not directly relevant to phenomenology, because unparticles, they usually have no gap, so no such a thing is not realized in nature. But then, of course, you can have gap unparticles, so that's the kind of scenario that we have over here, yes, where the continuum doesn't start at the origin, that doesn't start at zero energy, but starts at some relatively high gap, and then we have to figure out where the gap is. And in our case, what we are going to be looking for is a gap continuum that has, a generic kind of distribution, not something that is coming necessarily from in the form that our thinking about particles. All right. So how do you describe continuum states in general? So in this case, since I will be mainly talking about top partners, I was talking about fermions, and of course the whole thing can go through scalars and gauge bosons as well. Yeah? So what happens is that in your Lagrangian for the fermionic field, yes, you're going to get an additional form factor. So basically, the propagator is going to be modified, yes, and this additional form factor is of course related to the two-point function of these fermionic fields. Yes. And whenever you have a pole, yes, that would actually correspond to an ordinary particle. Whenever you have a branch cap, that will then correspond to a continuum. Okay. And the information, the actual information of sort of what would be the analog of the particle content is usually written in terms of the spectral density, which is the decomposition of this form factor that is given to the propagator, yes, in terms of, this is sort of the Galen kind of decomposition of the two-point function. In the spectral density, you can find this imaginary part of But again, the important thing is that this row, we have this spectral density, again, is what is telling you what is the content of your theory. Yes? So if there is a delta function here, yes, that is going to be an ordinary quantity. So then the question is, what kind of spectral density should be used? Yes, well, you could just make up a spectral density that is sort of phenomenology interesting, but of course we expect that there is a very large sort of using the popular name swampland of spectral densities. Most of them probably are not going to be coming from a unitary causal quantum field theory. Yes, so we don't know really, what are the conditions that are, you just take a spectral density, tell you that this is a good one, yes, this is not in the swampland, and which one is the bad one. So to be sure, what we decided is to go to a theory which we thought is, well behaved. So we were trying to get this from an extra-dimensional theory. And the reason for that is that there's, of course, the old story, again, that was worked out nicely by Giacomo and John and friends, that if you take sort of a vortex per dimension without an IR break, there will be a continuum of fermions without a gap, and that is basically like the story that Howard made up for unparticles. Okay? And so if you look at, just really truly, the original RS2 model, and look at the Green's functions on the UV brane, you are truly going to get an ungapped continuum in the Green's function. Okay. Of course, for us that's not good because we want a gap. The gap is essential. Yes, we don't want top partner continuum to start at zero energy. So we need to find a gap that is of the order of PeV or many hundred PeV. So what we did is we introduced an additional field, a scalar into the extra dimension. So we are going to call it the dilaton. It turns out later that it should be linear, and you will see in a moment why. And so this dilaton, what it will do is, around the UV brane, it actually is going to be very small, so it will have basically no effect at high energies, so it will still maintain, an ADS-like background here. But of course, close to the IR, yes, it is going to have some important effects. And you can think of this linear dilaton as modeling the details of the IR dynamics of the theory. Yes. So it's going to say, well, this is no longer the dual of a truly conformal theory. Yes, maybe it's a theory that gets close to the fixed point, yes, but then for some reason it gets a gap. Yes, that's sort of the dream that you have here for the EDS theory. Okay, so the nice thing about this setup is that actually the fermion equations of motion can be solved exactly if the dilaton is linear. So you can just go ahead and do the usual story, and I'm not going to go through the details because if you know it, it's boring, and if you don't, then you won't really learn, in 2 minutes how to deal with it. But it's a standard thing how to deal with fermions in vortex or dimensions. And now all you have is you're adding here the Mikava coupling to this linear dilaton, and of course, the background may also be somewhat modified here. Yes. So you can go ahead and calculate what the KK spectrum of the theory is. You will get an effective mass parameter. Those of you who did RS with fermions, remember what it is. Doesn't quite matter. The important thing is to get the spectrum of the theory. You will get basically a Schrödinger-like equation. Yes, so this one, everybody should recognize. This is like a Schrödinger equation, and there will be an effective potential here. Yes, that is going to tell you what the behavior of the spectrum is. Yes? So, as you know, just from ordinary Schrödinger equation, whether or not you get a gap in before you start a continuum or not will depend on what the potential asymptotes to at infinity is. If it asymptotes to 0, there will be no gap. If it asymptotes to some constant value at infinity, it's just an ordinary one-dimensional quantum mechanics problem. Yes? Then there will be a gap in the spectrum. Yes? So you can just go ahead and check, how does this potential look like when you go to infinity? And what you find is that in order for you to actually approach a constant at infinity, you will need one of these linear dilatons. Yes? And so that's why we are choosing the linear dilaton background for this theory. And in that case, again, the potential at will asymptote to some value that is proportional to the slope of the linear dilaton. Yes, so we want that to be of the order of a TeV. Yes, so we are going to be choosing the slope of the linear dilaton to be of the order of a TeV. Yes. And as I mentioned, the other nice thing about this particular linear dilaton is that you can actually solve the fermion wave functions analytically. Okay, some crazy functions. It doesn't quite matter, or Whittaker functions, but the important thing is that you can find an analytic solution, and the reason why this is going to be eventually useful is because we will eventually want to calculate the Higgs potential. Yes, these particles will be running in the loop, and having an analytic solution will make it much easier to eventually deal with the numerics. Okay, so, but the important thing is, so you can solve it. Again, it doesn't matter, exactly how you do it. It's a standard story for extra dimensional wave functions, and what you find is exactly that there's a gap, yes, and then you get a continuum, yes, and what exactly the shape of the continuum is will depend on this Yukawa coupling that you have introduced to the linear dilaton. Very good, and you can go through the exact same story for the gauge fields in the bulk. So you will find exactly the same story. You can find an effective potential there. It is also going to be asymptotic to a constant. So the KK decomposition for the gauge fields will also have a gap continuum. In this case, it's just literally starting with mu rather than there is no other parameter. So for example, this would be the spectral density for example, the blue one. Yes? So again, the expectation would be that there is no true KK modes anymore. There are no delta functions. There is just this very broad continuum that you're going to get. So now, to make a realistic model, of course, you have to somehow also introduce electroweak symmetry breaking. So for this, you do need to take all the known features of these composite Higgs models that people have been working on for like 10 years and or even a little longer. And so you have to introduce an IR brain, yes, because somewhere you have to get electroweak symmetry breaking. Yes, until now I didn't explain electroweak symmetry breaking yet, but again, that's basically completely standard. It's whatever people have been always doing in composite Higgs models. And so you introduce the IR brain. The Higgs will be just as usual, will be the fifth component of the gauge field, and basically you have to add all the known machinery that you do for composite Higgs models. There will be the usual bulk gauge group with minimal composite Higgs type of symmetry breaking pattern. On the UV brain, you will have some breaking by boundary condition, and on the IR brain, again, you will have the other boundary condition that is giving rise to electroweak symmetry breaking. You will have to have a bunch of fermions. Yes, so that's always the hard part of these composite Higgs models. That there's a large representation that you need in order to get the realistic fermion spectrum with some IR brain localized mass. It doesn't quite matter. Again, this is pretty standard. That's the only new thing that we are doing here is this linear dilaton that is going to modify the spectrum of the partners. Okay, so we found at least one realistic benchmark point. Audrey was working really hard for several weeks to get that point that all the standard model is pretty well reproduced, and it shows a pretty safe point at this moment because we don't quite have the exact bounds on the partners yet, but the gauge continuum starts at 1 TeV and the fermion continuum starts at 1.75. Okay, so we were able to get all the spectral densities for example, for the third generation, yes, again, it's a very complicated system because there are all these fermions in the bar, they will all get mixed with each other. So again, often have to diagonalize the cube. I think it was like 20 by 20 matrix. You get these crazy fractal densities. But again, what you see is that there is no sharp peak here. Yes, the strongest feature here has a width of several TeV at the order of 6 TeV. But in the regime that we are testing, yes, there is nothing that would be really standing out. Now, there are also some exotic top partners, and they are somewhat model dependent. Some of them could be, depending on the particular model, could be relatively narrow. So, but again, they are showing up at 5, 6 TeV, so probably not too heavy for the LHC. But it doesn't have to be. So changing the parameters of the theory could broaden these out pretty wide to make them pretty wide also. And in some cases, they are relatively narrow. And of course, the gauge boson spectrum, for example, for the gluon, will look like this. And so again, there's really no bump showing up in the gluon. So then, of course, the hardest part was to then go ahead and calculate what the Higgs potential is. Yes? So you have to feed in all of these spectral densities, calculate the Higgs potential, find a realistic model, and it's possible. Of course, there will still be some tuning there. Yes? So the tuning, the usual little higher tuning of composite Higgs models, this theory is not going to be solving. What it is solving is that, it's telling you that you shouldn't be looking for S-channel resonances. Yes? So for example, usually for the KK gluon, so this would be the production cross-section for the KK gluon. So you would see the bumps in normal, sort of ordinary composite Higgs models. In our case, yes, we have this continuum gluon, and what we have is just a very, just a rise over the standard model background, and this is something that's very hard to see. So, what will be the bounds on the theory? Well, we don't completely have everything fixed, but at the very least, what we know is that, of course, this KK gluon is this broad KK continuum is going to give a contribution to the running of alpha S. So that will set a lower bound on where this gap could be. So we checked that. So that's also something that is pretty well understood how to how these extra-dimensional theories are going to be correcting the running of the gauge couplings. So that gives sort of a lower bound on the gap for the KK continuum of the order of 600 TeV. But of course, that you have to compare with the 3 TeV type of bound that you had on the S-channel resonance. So the other thing that we haven't finished yet, and that's of course a very important question, and that's what Gabe has been working on for over the last year or so, is to find the production cross-section for the top partner continuum. And that's actually a really hard problem because we don't really know what the phase space of these continuum states is in general. Of course, the nice thing about particles was that George had found what the phase space is for those particular kinds of spectral densities. But in general, we don't really know how to do it. So we are resorting to the trick that John and Giacomo were using, which is to sort of use the optical theorem and try to calculate by a unitarity. But then you have to do a loop with these really weird objects running in it, and it looks like many of the Feynman rules are completely different than what we are usually used to. So that's what we are struggling with. So we don't really have a concrete bound yet on where the top partners, how light they could be, how much the bounds are going to be weakened compared to the usual top partners. So that's something we hope we are going to be finishing in a few weeks or months. All right, so in the last 5 minutes, I would like to just give you a slightly different new direction for composite Higgs models. So this will be ordinary particles, ordinary composite Higgs models, but there is sort of a new kind of symmetry that we were trying to employ. And as you will see, what this achieves is to basically get a particular structure for the Higgs potential that is different than what we are usually getting in composite Higgs models. It will actually minimize the amount of tuning that is needed, but otherwise it is an ordinary composite Higgs model. This is the work done with my friends from Beijing. So Ken is actually just applying for postdocs. He's a really very good postdoc of Jing, and of course Jing and Jian Hao are professors at the ITP in Beijing. Okay, so here the idea will be that so there's something called the maximal symmetry, which is a new kind of ingredient in composite Higgs models, which is basically an enhanced global symmetry of the composite sector. Yes. So what you usually have in composite Higgs models is that, well, you have, as I mentioned, there's a global symmetry breaking pattern. You break a global symmetry from G to H. And in the composite sector, because the global symmetry is broken, you only have an H symmetry. And the composites, they don't even have to form multiplex of the original G symmetry. Okay? However, there's nothing that tells you that they couldn't possibly have a bigger symmetry than that. It depends on the dynamics of the fluid. There could be an accidental emerging symmetry in the composite sector. Yes? And what we are saying is that that accidental symmetry, if it's there, yes, again, it depends on what exactly the dynamics of the theory is, could have important consequences on the Higgs potential and on the tuning of the theory. Okay, so the best way to see, where this maximal symmetry is showing up is by looking at the Goldstone matrix. Again, that's of course always the key in these composite Higgs models. And as you know, this Goldstone matrix, yes, has a weird transformation property. So from one direction, it transforms, just with the ordinary unbroken global symmetry linearly. Yes. From the right, it transforms with, an element of just the unbroken gauge group. Yes. And that's where the nonlinear realization is coming in. Yes. This unbroken element, gauge element, yes, is of course nonlinearly dependent on which element you are exactly talking about. So the best way to think about this rule is to say that actually, this Goldstone matrix connects the elementary and the composite sector. So you can think of this G as the elementary SO5, elementary symmetry, and then on the right, this H is sort of an element of the composite global symmetry, which is of course broken down generically to some smaller sum. So what we are asking is that is it possible that there's some remnant of this bigger global symmetry that is remaining unbroken, which can protect the Higgs potential from the corrections. Okay. Now it turns out if either of these elementary or composite SO5s is completely unbroken itself, that's big enough to completely set the Higgs potential to zero. So you definitely don't want that, because in that case, the Goldstone matrix will completely disappear from your effective Lagrangian. There's no potential generated, and that's of course not a realistic theory. Yes? So we need to break the symmetries, but such that there's some remnant that is left over, which is not equal to the original, these global symmetries that you have started out with. Turns out that, for example, in extra-dimensional theories, this is something really easy to do, as it just depends on what boundary condition you're going to be imposing on your fermions on the IR brane. But let's just step back and see from sort of the bigger picture. Again, the standard assumption is that the standard model fermions are elementary, so they are embedded in the elementary sector. Yes? And this embedding itself is usually enough to just break the elementary global symmetry sufficiently such that you don't have to worry about those. Okay? Now, in the composite sector, again, this is the tricky part. Yes? What you want is you want to maintain an SO5, but it shouldn't coincide with the original SO5 of the composite global symmetry. Yes? So how can I do that? Yes? So let me give you the simplest possibility that is hopefully easy to understand. Yes? So again, to begin with, there's no reason for the composites to fill out a complete representation of SO5. If they don't, there's no additional symmetry and they have nothing to say. But sometimes they do, yes? So we will assume that the composites form basically a complete 5 of SO5. Yes? So that will be composed into a 4 and a 1. Yes? So that would have then, without any masters, would have SO5 left cross SO5 right global symmetry, chiral global symmetry. And then depending on the particular structure of this singlet and fourplet master, yes, you will have different breaking patterns. Okay? Now, of course, you can have these masses to be equal to each other. In that case, actually, you are breaking, the unbroken global symmetry will be the original SO5 composite global symmetry. And again, that's nice, but it forbids the Higgs potential completely. So it's too strong. Yes? There's a second possibility. This is the interesting one. Yes? Where you sort of, have these masses equal to each other, but have the opposite sign. In that case, there is sort of a twisted SO5 that is left unbroken in your composite set. Yes? And this is another SO5 that is not identical to the original SO5 that you started out with. Yes? And this SO5 will then be the one that is going to be protect your theory from quadratic divergence. Okay? And then, of course, in the generic case, you are just back to SO4, and then this is just a generic composite. Okay, so amount of time, so I'm not going to say a whole lot more about this, just that you can have this additional global symmetry. And this additional global symmetry you can go through and show that you'll have a very important consequence that when you write down the effective theory for the standard model fields in terms of form factors, you'll actually kill one of the form factors. And it will kill exactly the form factor that is the most dangerous from the point of view of quadratic divergence. Any quadratic divergence and log divergence is always proportional to exactly the one form factor that you can kill with this maximal symmetry. So if you have this maximal symmetry of theory, you automatically have a finite non-vanishing Higgs potential. And what is even more interesting is that you'll have a particular form of the Higgs potential, and I'm not going to go through the details, but basically it will automatically give the minimal tuning that you can possibly have in composite Higgs. Okay, so I'm going to skip the particular models. So we have particular implementation, so this is not just symmetry, I'm going to get particular simple model. There's a symmetry and it gives rise to the potential. You can go ahead, calculate the tuning. It is going to be the minimal amount, but it will have important specific consequences. For example, the fact that you have a complete SO5 multiplet will tell you that you will have to have 3 top partners. There will be particular relations among the Yukawa couplings. Again, all of them enforced by this maximal symmetry. There will be some sum rules that you can verify at a very high end equalizer. Conclude. All right. So composite Higgs models, there are favorites. One of the favorites is solve the hierarchy, but of course, they are all worrying about the fact that we haven't seen these top and gate partners. One of the directions that I was trying to explore is that maybe the reason why we haven't seen them is because they are actually continuum states rather than ordinary particles. So they would be harder to see, there would be no external resonances. And I showed you a complete realistic model that is based on the linear electron. Okay? The other direction that I was telling you about composite Higgs models is the idea of maximal symmetry. So in this case, there would be an accidental symmetry in the composite sector that would have additional consequences on the structure of the Higgs potential. It will soften, the divergences, minimize the tuning, and actually there will be many other uses of the symmetry that we still have in our bag and we are going to be exploring. All right, thank you very much.
I have a couple of questions about the continuum models. So you said that they have 1% tuning, so they don't solve the little hierarchy problem any better than regular composite Higgs. But so what they do is to evade collider bounds, perhaps. Although
right. So for at least we are pretty sure that for the KK gluon they do. Now for the top partners, we are not sure yet how much, yes? Because things like same sign dileptons, that's not anything that's a bump hunt probably is going to be there, yes? But not all bounds are bump hunts, yes? So that's why we are trying to really calculate as I mentioned, the production cross section for the top partners and see how much is that. Of course, what I could do is I could just push the spectral density more and more towards the high end. But that's really cheating in the sense that if I have the top partners sort of peak at higher and higher values, I'm sure the production cross section is going to go down. But then the cancellation of the quadratic divergences will also be affected.
Are you including that in your tuning calculation?
Yes.
Okay. Right. So you can't do that forever, I guess.
Right.
But I guess my question is, what is the tuning being driven by in the regular composite Higgs models? Is it the bounds on the KK gluons and top partners, or is it just the Higgs precision measurements and things?
Right. So I
Higgs
think
coupling measurements.
it's right now at the stage where they are starting to be comparable.
Oh.
I think as long as the top partner bounds were below a TeV, it was still just driven by that. Now that it's around 1.5, we are starting to see that the two are roughly starting to be comparable. It may still be, I haven't checked whether it's still flat or.
So you mentioned that in this model also the top is slightly like how
Right,
can you fix it?
So it's
in the
slightly
wrong
lighter,
direction?
just for a technical reason, because the point where you have it's not like you cannot have a realistic top mass. It's just very hard to because the theory has a tuning. It's harder to find those points, and those are more rare. So we just didn't find. We don't think that this is anything specific to this particular model. Okay, this was exactly the same as the usual composite model. Those points are just more tuned, and they are harder to find. So we didn't want to spend months on finding that particular point. But we don't think there's anything fundamentally predicting it to be very light, the top to be very light.
Okay, so what might be the problem? So if you say let's say fix the top mass.
Again, it's just technically harder to find. I mean, you have that point is slightly more tuned, so it's much
it's
more.
Just slightly.
It's just numerically harder to find that realistic point because it's much more rare. We didn't do a really strong scan. Yes.
For continuum states, I suppose there's still a cutoff in the model. Usually, how you deal with the for example, the iterative for the states near the cutoff.
Right. So this is again this is coming from a higher dimensional theory. Yes, there is an underlying higher dimensional theory. It has its own cutoff. So that's what we would be expected to be. Yes. And we wanted it to come from a higher dimensional theory again, just because we were not quite sure what the rules are for postulating an arbitrary spectral density. When does it make sense, and when do you really badly break unitarity already at a low scale? We don't have a good intuition on that. I'm sure there are probably rules for that, and maybe the theorists who have done more about CFPs maybe they know what are the good spectral density. So we wanted to be safe, so just let's take it from a 5-dimensional theory. We think it's probably everything is under control.
Sorry, one quick question. So traditionally, when we talk about dilatomes, there might be possibility in mix with the same model of Higgs boson. Is that the case in your?
So we haven't looked at that. It's very possible, of course. Yes.
Okay,
So we haven't looked at that. Yes. And we haven't looked at the radial. We haven't really looked at the stabilization. There's just sort of the first iteration of checking. Does it even go in the direction that is sort of interesting? Yeah, there are many other things to do. There's a radion here, because there's an IR grid. You probably have to add it over the device field. You want to also the most important thing that we haven't done is, yes, so this linear dilaton should have a slope of the order of TD, yes. So something needs to explain why that slope is TD, yes. You think that, probably coupling it to the rotor of the right field, you'll probably be able to do it, but we haven't tried to solve all of those couple of equations, so that's still an important thing that is needing to be done.
Yeah, that was my second question, I guess, is so is mu radiatively stable, or?
So again, so for now, we just put it in by hand. Yes. We expect that it shouldn't be a problem because, again, we have an IR grade. We are not claiming that mu is the solution of the hierarchy problem. Yes, we have an IR grade. We have to stabilize it, and we are expecting that the mechanism that is stabilizing the IR grade will probably also, be able to give you a mu of the order of TD, but again, it's something that has not been done.
Last question?
Yes.
So one question about the 5D models. I mean, linear dilaton backgrounds in ADS are not usually dual to local quantum field theories. They're dual to little string theory or something of that sort. So why do you think this gives you necessarily a good spectral density, this approach? Because presumably you want your theory to be a local QFD.
Why it gives me a good spec? I mean, we can calculate what the spectral density is.
Right, but I mean, I thought your motivation for going to 5D was that you weren't sure which spectral densities would, right? But I mean, the thing that is dual to a linear dilaton background in ADS is not a local QFD. It's a string theory.
So that's okay.
Okay.
Do you mind if it's a string theory? What I meant by that is I don't want it to be an inconsistent.
I have a question, but the time is tight, so I will